Hey guys, welcome to week 4's lecture of the Competitive Programming Club. My name is Luke, a VP academic for the club, and today I'll be presenting to you guys a well-known topic in the world of competitive programming and technical interviews, and that's going to be trees. Whether you've taken an algorithms and data structures course previously or are new to programming, this lecture should be able to give you a good refresher or introduction to what trees are and what types of trees are commonly used. So let's get right into it. To start off, let's look at what a tree is in programming. We can simply think of a tree as a nonlinear data structure with a parent-child hierarchy. This means that every child has exactly one parent node, but parent nodes can have multiple children. So for example, if you look at this node, it has exactly two children node, but you can see that any single node in this tree only has one parent. So for this node, there's only one parent over here. For this node, there's only one parent. For this node, there's only one parent. And as you can see, each node can actually act as either a parent and a child. And that's evident when you look at this node. This node acts as a parent for these two nodes, but acts as a child for this node over here. Many of you may know that graphs are also a nonlinear data structure consisting of nodes. And you can simply think of a tree as a special type of graph. We typically call the very top middle node of a tree a root node, and call the last node in a branch sequence a leaf. So as you can see here, this would be called a single branch sequence, and you can see that at the end of the branch sequence, the node that doesn't branch out to anywhere else is called the leaf node. You can sort of visualize a tree structure in programming as an upside down tree, as the root is on the top, and you can see that the leaves are typically at the bottom of the tree. Trees are most popular for simplifying and speeding up searching and sorting. It is regarded as one of the strongest and most advanced data structures. This all comes from the fact that it's a hierarchical or nonlinear data structure. Compared to arrays and linked lists, which are linear data structures, we'll be taking advantage of this unique structure in order to make faster sorting and searching. We'll be going over the procedure for sorting and searching during this lecture as well, so sit tight. Before we get into the different types of trees, I wanted to pause and show you guys what a typical node of a tree may look like. This code right here is in Python, and we can see that in a single tree node we have the values val, left, and right. Val will essentially contain the actual information that the node contains. So if you look at this node, for example, it would contain the number 5. Left will contain a reference to the left child node. So for example, this would be what is being referred in this node for the left value. And right will contain a reference to the right child node. So for instance, this would be the right referenced node for this node right here. The first tree we have here is a binary tree. Most trees are actually derived from a binary tree, which is why it's regarded as the most basic and most popular tree. Some of the derivations here we have is binary search tree, AVL tree, and red and black tree. We'll be going over binary search tree and AVL tree this lecture, but unfortunately due to time restrictions, we won't be able to go through red and black tree. It follows the parent-child hierarchy as I mentioned earlier, but a parent can have at most 2 children, as you can see here. You can see that there aren't many restrictions on the binary tree other than the fact that each parent can have at most 2 children, which is why the trees that are derived from it simply have more restrictions that make it specialized. To start off with the most simple derivation, we have a binary search tree here, or also known as a BST. You can think of a BST as a binary tree with several restrictions, such as the left child having to contain a value that's less than or equal to the parent value, and the right child having to contain a value that's greater than or equal to the parent value. It's actually completely up to the programmer to decide on how their BST will handle equal values, so they can either choose their code to insert equal values on the left or the right, and either would be considered appropriate. In retrospect, a BST is simply an ordered or sorted binary tree. With these restrictions, a BST is able to handle searches and inserts much faster than most data structures. Let's take a look at some pseudocode for these operations. Here we have some pseudocode that searches for a specific node in a binary search tree. When imagining this as a function, we can assume that we're passing in the root node as our input. The target value here is 4, so let's see how this algorithm works to find it. I want you to pay attention to why this might be done in O of log n as mentioned above. So we first start off checking if the root node is equal to the search node. So we're essentially checking if 7 is equal to 4, which it is not, so we basically go into the else conditional. In this else conditional, we're entering a while loop that runs until the data is found. The first condition we're going to check is if the data is greater than the root node. So we're checking if 4 is greater than 7. And in this case, it is not, so we go into the else conditional that makes the node go to the left subtree. As we see here, we've moved to the left subtree and we've completely disregarded the right subtree. I want you to pay attention to that. So now when we go to this if statement, we can check if the data is found at this node. 3 is not equal to 4, so we're gonna go back up and go through another iteration of the while loop. So going through the same sort of conditionals, we can see that this time 4 is greater than 3, so that's how we went down to 5. Again, the data is not found at 5, so we go through another iteration. See, in our last iteration, we can see that we went to the left subtree since 4 is less than 5, and we can see that we found 4, and the algorithm will finally terminate. So why exactly is this a time complexity of O of log n? What I want you to realize is that we continuously divided up our sample space as we went further down the tree. In our initial root node, we completely disregard the right subtree over here, consisting of nodes bigger than 7, because if we know that our target value is less than the root value, there is no way that the value will exist on the right subtree of the root, since we know for a fact that the nodes on the right of the root are all greater than the root's value. So for example, you can see that 8, 9, 10, 11, 12, 13, 14 are all bigger than 7, and there's no way 4 has any space to exist in this space, assuming that this is a binary search tree. And we start out with 15 nodes. So the total amount of nodes we have here is 15. Then as we disregarded this right subtree, we finally came to 7 nodes. Then we divided up another time going to the right subtree. Now we have 3 nodes. And then finally we have 1 node, which is our target node. And the amount of divisions it took to reach to our target node was 4, which is equivalent to log base 2 of n. Essentially, the question we're asking ourselves is how many times did we divide our original list size in order to get to our target value? When we look here, we can see this in sort of a mathematical equation. We can see that n is being divided up however many times in order to get to a list size of 1, essentially meaning that we found our target node. So this can be represented as n times 1 over 2 to the power of x. We can sort of multiply this in, and then we do some algebra to rearrange this in order to see that we have a relationship saying the number of nodes equals 2 to the power of x. Now if you apply log base 2 on each side, we get the equation log base 2 of n equals x, which is essentially the equation that we have here. Now this isn't always necessarily the case, and I want you guys to think about why that is. We'll go over the answer after I showcase the insertion algorithm for a binary search tree. So for insertion, I have an example here where we're inserting the node of 15 inside the same binary search tree that we saw earlier. Evidently, inserting in a binary search tree is going to be similar to searching in a binary search tree, just with a few tweaks. As we can see here, this is going to run at a time complexity of O of log n as well. So we first check if the root node that we got inserted, or we were inputted with, is null. This means that we have an empty tree that we got, which means that we can simply make 15 our root node, and then we can terminate the program. Or else, if the root exists, then we start comparing the data with the inserting node that we have. So we first check if 7 is bigger than or smaller than 15. As we have here, we have a similar while loop as we had earlier. So we first check, we know that 15 is bigger than 7, so we're going to be traversing down towards the right subtree. And this time we're going to be completely disregarding the left subtree. So now we make a similar comparison again with the if and else conditional. We see that 15 is greater than 13, or 15 is greater than 11, so it goes down to 13. And again, 15 is bigger than 13, so it goes down to 14. And once we've located a insertion position, in other words, a position where a node doesn't exist and 15 can be inserted, which is sort of the right child of 14, since 15 is bigger than 14, we can see that we can make the insertion and we can terminate the program right there. So now let's take a step back and see what sort of cases there might be where this average time complexity doesn't exactly apply. And that's when we have a linear list like this. So imagine that we had a root node of 1, and then we started inserting 2, 3, 4, and 5 respectively. This essentially looks like a linked list, and we'll have a time complexity of O of n for insertion and searching. This is because we have a linear structure now instead of a hierarchical structure, which we were trying to avoid originally. So this is actually a difference between a balanced and an unbalanced binary search tree. So the tree on the left is considered balanced, and the binary search tree on the right is actually considered unbalanced. So what exactly classifies these two trees? And the answer is the height of the tree. You can see that the height of the tree over here is notated by log of n being the number of total nodes, and over here the height is simply n, again, which is the total number of nodes in the tree. We never want this happening in our binary search tree, or else searching. So for example, if we're inserting 6, we would have to go through each node of the tree, which would essentially make it the same time complexity for inserting as a linked list, and we don't want that. Similarly, for locating the node 5, we would have to go from 1, 2, 3, 4, 5, looking at every single node in the tree, and we don't want that. The whole point of this binary search tree is being able to search and insert with a time complexity of O of log n. So let's take a look at some methods that will help us convert an unbalanced binary tree to a balanced binary search tree. The main method we're going to be looking at is rotations. The goal of rotation is to decrease the height of the tree by rearranging subtrees. The key here is that we're not affecting the order of any elements, since we're simply changing a couple of references in our tree. In other words, we're simply rotating around a specific node. To better understand the concept of rotation, we'll be taking a look at the AVL tree. AVL trees are essentially a binary search tree that uses rotations to balance itself. In other words, the tree ensures that we don't end up with the unbalanced binary search tree as we saw earlier. It takes a look at the balance factor in order to determine whether or not a tree is balanced. So the balance factor can be calculated by taking the left subtree height and subtracting it by the right subtree height. The tree aims to maintain a balance factor of either -1, 0, or 1. If it finds that it doesn't have this balance factor, it will perform rotations in order to balance itself. So if we look at this tree right here, we can see that the left subtree height is 1 and the right subtree height is 1. 1 minus 1 equals 0. This tree is balanced. When we look at this tree, we have a left subtree height of 2 while we have a left subtree height of 0. 2 minus 0 equals 2. This exceeds our bounds of our balance factor, so this tree is deemed unbalanced, and the AVL tree will perform rotations. Similarly, for this tree, the left subtree has a height of 0, and then the right subtree has a height of 2. 0 minus 2 is -2, and similarly, the tree is going to perform rotations. Let's now take a look at the types of rotations that an AVL tree is able to perform. So first of all, we have a left rotation. This rotation is applied when a node is inserted in the right subtree of a right subtree. So for example, if we already had the tree AB, C was inserted in the right subtree of A and on the right subtree of B. So in this example, we see now that root A has a balance factor of 2 after we inserted node C. By rotating the tree left, we can see that node B becomes the root, resulting in a balanced tree. Next up, we have the right rotation, and we can see that the right rotation takes a similar approach as a left rotation, but rotates right whenever a node is inserted in the left subtree of a left subtree. So I won't be going over this again since it takes a similar process. Now let's look at a bit of a more complex rotation, which is called the left-right rotation. We can see in this example that node B has been inserted into the right subtree of the left subtree. This makes node C have a balance factor of 2, thus making the whole thing unbalanced. So we first have to perform the left rotation on the left subtree of node C. So this makes node A the left subtree of B. So essentially B goes to where A is, and then A goes to the left subtree of B. So it looks like this now. And now we can still see that node C is still unbalanced. However, now it's because of the left subtree of the left subtree. And we saw earlier that we simply just have to make a right rotation at this point. So once we make a right rotation on the node B, we can see that the new tree looks like this, having a balance factor of 0 all around, and thus the tree is finally balanced. Then lastly, we have a right and left rotation, which is simply what we just saw earlier, but with a right rotation first, and then a left followed by a left rotation in order to balance it finally. So now let's take a quick review at what we've learned today. So first, we looked at what a tree looks like as a data structure in programming, and then looked at the two most basic trees, which are binary trees and binary search trees. Then we looked at a typical algorithm for searching and inserting inside of a BST, where we located a vulnerability with unbalanced BSTs. Lastly, we took a look at AVL trees, which is a self-balancing BST that prevents unbalanced BST from occurring. And then looked at the 4 different types of rotations that they perform. And that concludes our presentation. For the beginners starting out, in order to familiarize yourself with binary trees and binary search trees, I recommend trying these following questions on LeetCode. These questions will allow you to better understand how to traverse the tree and make different operations along the way. For the others, I recommend you check out our weekly contests for more complex tree questions. If you have any questions, please leave them in our Discord and I'll be happy to help. Here's a link to our Discord and some of our other socials if you're interested. The contest will be posted shortly in our Discord server, so I suggest you join if you haven't joined already. As next week is reading break, I'll be coming back with another lecture on February the 24th. Well, that is it for today, and thanks for tuning in, and I hope you have a great rest of your day.